Hello everyone, and welcome to the fourth FoCM online seminar. My name is Markus Bachmer and I will be chairing today's session. Our first speaker today will be Carola-Bibiane Schönlieb, then followed by Bojan Mohar about 1 hour later. A brief remark on the technical side. The session is recorded and also streamed live on YouTube, and the video will be made available also on the FoCM YouTube channel. If you would like to ask a question after the talk, please raise your hand. And we will then ask you to unmute yourself, and then you can also switch on your video if you like to ask the question. In addition, you can also post questions in the chat, also at any time during the talk, if there's some urgent question. Now, without further ado, let's come to the first talk. And it's a great pleasure to announce Carola-Bibiane Schönlieb. She is Professor in Applied and Computational Analysis at the University of Cambridge, head of the Cambridge Image Analysis Group, and fellow of the Alan Turing Institute. Her work spans image processing, partial differential equations, inverse problems, and also machine learning. And she has received quite a few honors for her work, among them the Whitehead Prize in 2016, the Leverhulme Prize in 2017, and also the Calderon Prize in 2019. And today, she will speak on machine-learned regularization for solving inverse problems. Please, Carola.
Thank you so much, Markus, and thank you to all the organizers for inviting me to give this talk. It's really a pleasure. Can you see my slides?
Yes.
Okay, thank you. Great, that's good. Okay, so Markus already mentioned the Cambridge Image Analysis Group, and indeed these are the first ones that I really would like to express my immense thanks to. Without my group members, what I'm going to talk about today would have never been possible. They have really made some tremendous contributions, and they're a wonderful group of people. So thank you very much. And also thanks a lot to all the sponsors from government, from private trusts, and from industry who are sponsoring our research. Thank you. All right, so the main ideas that I would like to bring across in today's talk are as follows. First of all, deep learning, deep neural networks, I strongly believe, offer very interesting opportunities for inverse problems, mainly because of two things. First of all, with neural network type of approaches, we can compute very high quality solutions to inverse problems, making use of the capability of neural networks to be very data adaptive, to represent, to capture, structure information in data that delivers accuracies in solutions that were previously really unseen. And there are lots of examples, and I'll show you some. The other really interesting thing about neural networks is, in really contrast to most inverse problems solutions, is that they're computationally efficient once they're trained. It's just an explicit application of linear and nonlinear operations that we need to perform. They only work in practice when combined with mathematical and statistical modeling. And in practice, I really mean beyond toy examples, but really working for real world problems. And this is kind of linked to this still, even when linked with mathematical statistical modeling, existing approaches that are based on deep neural networks, most of them we lack understanding for what they're doing, and they really require more mathematical scrutiny. And so one of the main type of neural network approaches that I would like to discuss today, that kind of takes a middle way between mathematical soundness and these wonderful properties of deep neural networks of being very data adaptive and being computationally efficient, so that takes a middle way between empirical performance and theoretical guarantees, are learned variational models. And those are the ones that I'm going to focus on. And in particular, focusing on using deep neural networks to parameterize and learn the regularization, make the regularization data-driven. And I'll clarify this in a moment. And maybe also to say that most of what I'm going to talk about today really has been also triggered by a review paper that we have written 2 years ago, together with Simon Arich, Peter Maas, and Ozan Öktem, on this topic of data-driven inverse problems. Okay, so let's recall what an inverse problem is, and in particular, what an inverse imaging problem is. So in short, I want to compute an image, U, that lives in some normed vector space X from measurements Y that are connected to the image U through a linear or nonlinear operator capital T that is also called the forward operator, and that are corrupted by measurement noise, okay, by random noise. So a typical example, prototypical example for an inverse imaging problem is computer tomography, which I'm also visualizing here in these 2 pictures, where the forward operator T is the X-ray or radon transform. And the measurements Y in this case are line integrals at different angles, which is this axis here, and different Y-intercepts through the image function that I have here on the left. Okay, so what I'm doing is when I'm acquiring a CT measurement, roughly speaking, is that I'm integrating at different Y-intercepts and at different angles through this image function U. And in the X-ray context, you can think about this as the line integrals representing the accumulated attenuation that the X-rays are experiencing when they are traveling through the object that is being imaged, through, in this case, the human body. And the image function that we reconstruct then kind of relates to the X-ray attenuation or the tissue density that has caused the X-ray to attenuate, okay? So the forward problem is usually knowing the image U, compute the measurements Y. This is called the forward problem, and that is usually the problem that is the easier one, in the sense that the only thing we need to be able to do is to simulate computationally this forward operator capital T. Yeah? And this is most of the time okay. I mean, inverse imaging problems are very large, so this could still be computationally heavy, but that's okay. The much harder problem in general is the inverse problem, which is also the practical one, based on the measurements that I have here on the right. I want to reconstruct. We very often speak here of reconstruction. We want to reconstruct an image U that has caused these measurements, that is the source of these measurements here on the right. And this is harder because of most of the time these inverse problems being ill-posed, mathematically ill-posed, because of the inversion of this forward operator capital T, the inverse being unbounded or being discontinuous, and this happens a lot of times in inverse imaging problems, the data being corrupted by measurement noise, and we are undersampling. Undersampling meaning, for instance, in the CT computer tomography context, that we measure less than we actually have unknowns in the image, which means number of pixels in the image. And measuring less in a computer tomography context usually means sparse angles, so less angles, or less lines per angle. okay, which depends also a little bit on the properties of the computer tomography machine. Okay, so these are usually ill-posed problems, and computer tomography is just one example. Capital T in inverse imaging, for instance, in magnetic resonance tomography, can also be the Fourier transform or a subsampling of the Fourier transform. We will see this actually in one of the examples that I'm going to show. Capital T in the nonlinear case, if capital T is a nonlinear operator, could also be a PDE, for instance. Or something like this could be also a function that maps to the boundary of a domain. If you only have measurements at some boundary of a 2- or 3-dimensional domain where you want to reconstruct the function, and so on and so forth. There are lots of examples. Now, a typical approach in mathematics to turn those problems into well-posed one is through regularization. And a standard, a very widely used set of approaches of this type are variational regularization approaches. And so here, an approximate solution to my inverse problem is phrased as a minimizer of an energy functional that on the one hand captures the data model, so my forward model and its fit to the measurements. And this is also called the data fidelity, data discrepancy term. And very prototypical choice for this data discrepancy term is a least squares fit. The particular choice of the metric that is used here is usually driven by the statistical properties of the measurements. And then this data discrepancy term is complemented by a regularization term that I call here R of U, that is turning this ill-posed problem into a well-posed one that regularizes the solution, and that you can think of incorporates all the prior assumptions that you have of the type of solutions you want to compute of this inverse problem. Yeah? And a very typical prior assumption that holds for images is that edges are very important in images. And so this is why, as a regularization, the total variation has had huge success in inverse imaging problems, as it is one prototypical edge-preserving regularizer. Yeah? And I'll show you briefly on the next slide. And then these two terms, the regularization against the fit to the data, are balanced against each other through a regularization parameter alpha. Okay, so the larger this regularization parameter alpha, the more I regularize. So the more I need to counter the ill-posedness of the forward operator T and the measurement noise. Okay, so let me just briefly show you what this regularization is doing by means of looking at total variation regularization for image denoising. Okay, so simple example where the forward operator capital T is just the identity. So what I want to compute is a denoised image, an approximation to the clean image from a noisy measurement of the same. And I do this by, roughly speaking, denoising, smoothing the noisy image with this total variation penalty, which you can understand the effect of when looking at the corresponding steepest descent or gradient flow, subgradient flow of this variational problem. The total variation is not differentiable, so we are looking at a set-valued gradient that we can compute of this functional, of this energy. And if you look at this and you pick a particular subgradient for which the modulus of the gradient of u is not 0, which means you are out of your non-differentiable region, then we can look at what this nonlinear diffusion that is induced by the total variation is actually doing. Namely, it's regularizing, it's smoothing, it's diffusing the image with a diffusivity, with a scalar diffusivity function that is weighted as 1 over the modulus of the gradient of u. So it diffuses more when the modulus of the gradient of u is small, and it diffuses less if the modulus of the gradient of u is large, is where the edges are. And you see this here also in the simulation that I have produced here on the bottom, where I initialize this flow with the noisy image at time t equals 0. And then I overdo it. I choose a very large regularization parameter just so you see the regularization effect even more clearly. And then I show you here the iterates. Okay. So this is just one example of such a regularization term, and there are many more. There are many more, like, if you think about multi-resolution analysis, where people are looking at sparsity promoting priors, L1 norms of wavelet coefficients, or any kind of other Banach space norms. There are tons of different nonlinear PDEs that people have considered for regularizing inverse problems. Anisotropic diffusion, non-local diffusion approaches, and so on and so forth. Yeah? So there is a huge family of things that have been proposed. And these really work, yeah? And I'll take this as an opportunity to show you a little bit of the portfolio of things that you can do with this, of some of the things that we are interested in the Cambridge Image Analysis group, which really are extremely diverse and can really help you to solve real-world problems. So what you see here is an example from computer vision. This is a detection, classification, tracking problem where we are looking at video data and want to quantify traffic and stratify traffic in urban areas in urban areas in India. This is a project together with some colleagues of us in Delhi. Again, variational approaches are a core component here. The variational approaches are integral also for various problems in image processing, in image manipulation. This is an example from a digital art conservation project with people from the local museum here in Cambridge, where we want to remove over painting in illuminated manuscripts. Biomedical imaging, we have seen computer tomography as one example. There are many more. There are many more kinds of tomographic imaging that are used in a medical context. Think about positron emission tomography. We mentioned MRI. There are lots, ultrasound, for instance, and so on and so forth. And even when you think about inverse problems where you are inferring based on a set of images, so you want to make inferences like clinical decisions, diagnostic or prognostic predictions you want to make based on imaging data of patients. This is again an inverse problem. And again, variational type of approaches, partial differential equations, play a major role in solving all of these different types of problems. Going back to CT though, there are limits of these type of mathematical regularization models. And this is now a simulated example. Yeah, so we have a CT image that we have reconstructed from full angle, so fully sampled angle, very low noise measurements, yeah, which usually means high dose X-rays. So we have this is the image I call ground truth. I'm simulating clinically standard clinical measurements, so the kind of measurements you expect in a clinical setting to encounter, which are high noise, so low dose measurements. And what you see here in the third, fourth, fifth, sixth, and sixth image are reconstructions from these realistic type of CT measurements that are simulated from these ground truth. Okay, so high noise measurements. And the first two are based on mathematical models that are similar to the ones that we have just encountered. This is called filtered back projection. This is total variation regularization. So this is a minimizer of such a TV regularized problem as we have seen on one of the previous slides. And the last three are deep learning based solutions. Okay. And so what you see here, and I like this example because I think it's quite obvious, is that there is a huge jump. There is a huge jump from both in terms of visual quality of the reconstructed images, as well as in terms of quality measures compared, so similarity measures with respect to the ground truth. And these are the numbers that I'm reporting here at the bottom of each of the images. The first number is the so-called PSNR, peak signal to noise ratio. The second one is the structural similarity index measure, and both should be high. So the higher, the better. Yeah, and you can see a tremendous jump if you go from the top to the bottom. So how does this work? Yeah. So what can we say about that? So brief comment about deep neural networks, just so we are on the same page. So a deep neural network is a collection of generic layer functions, FK, that map a feature space and a parameter space into another feature space. Okay, and we can usually think of having, let's say, if you have a K layer neural network, you have capital K such layer functions. You start in the first layer, you start to initialize your feature vector with an input that could be an image, for instance, that I call little x. And then I feed this input through my layer functions that are combining this input with, in what way we will see in a moment, with these parameter vector theta k. Okay, and in the end, I get out a feature vector, so some transform of my input image, let's say, that I call Z capital K, and this is the output of my network. So the output of my network is what I get after iterating these layers for capital K times. Okay. All right, so let's look at a particular example. So if my layer function f could, for instance, be, and this is a prototypical example, an application of a linear function, a matrix A to my input Z, plus a vector B that is also called the bias, and a nonlinear function sigma that is usually a nonlinear, that is usually an element-wise nonlinearity that acts element-wise on these vectors here, and that can have many forms. Yeah, so ReLU is something that many of you have heard about, tangents hyperbolicus, and so on and so forth. A is often replaced by a convolutional operator because of computational issues, because of computational demands, because the parameter vector theta is now the vector A and the matrix A and the vector B. And so all these make up what happens to my input. And now the training goal, or what we mean when we talk about deep learning, training a deep neural network, is that we are looking for the best parameters theta, so for the best matrices A and for the best vectors B, such that if I look at the result of this neural network that is made up by these parameters theta, and that I feed with input vectors, with input images xn, that they produce an output that is small with respect to some loss function. Okay, and this loss function could, for instance, be in a supervised deep learning setting, the fit of the output here. This is the output of the last layer against a training set of desired outputs that I call here yn. Okay, and then I could also have some regularization on the parameters. Yeah? So this is the typical kind of deep learning setup. I have a training set of examples of typical outputs and inputs of this neural network, and I want to train the neural network. When I train the neural network, it means I optimize over the parameters that make up this neural network. Now, how can this be used in the solution for inverse problems? And so I give you some examples now of how people have thought about doing this before I converge, and I want to spend most of the time on showing you how to learn, how to use neural networks to learn the regularizer in a variational context. Okay, so the main paradigms. First one is fully learned models. Fully learned models means that the whole process of measurements that I take to reconstruction is modeled by a neural network. Yeah? So this is here looking at an example of magnetic resonance tomography, where the forward operator capital T is the Fourier transform, or is a sampling operator applied to the Fourier transform. So what I'm measuring are frequencies of the image I want to reconstruct. And so if you look here at the visualization of the measurements that are taken by the magnetic resonance tomograph, this is Fourier space. This is the center of Fourier space. So these are the low frequencies, and if you go out, you're looking at higher and higher frequencies. And we have discretized this of the Fourier space with n cross n. With n cross n points, matching the dimension of the image I want to reconstruct. But I'm not measuring all of the Fourier coefficients in this discrete Fourier space. I'm only measuring a subsample of those. I'm measuring like 20% or something like this of the overall number of Fourier samples that make up the image. And I'm sampling and imaging because of time, because I don't usually I'm conditioned by how much time my measurements can take. No? And so what is being measured here is visualized in white. And now the task is to go from these frequency measurements to an image. And so what I first kind of need to do is I need to go from my frequency space into image space. These are the things I need to do. I need to invert the capital T, and I need to regularize, because although the Fourier transform is a nice isometry, I'm not measuring all my Fourier coefficients. So I also need to make up for that by doing some kind of interpolation. You can think of the regularization doing. Yeah? And so in the neural network, I need to do, on the one hand, the global transformation, which is here modeled by fully connected layers. I need to do something that brings me from Fourier space to image space as a global transformation. So this is where I need full matrix multiplications. And then I need to regularize. And this is here modeled by these convolutional layers. Okay. Now, how does this work? This is now an example where one of the first examples of such a fully learned model called AutoMap. where they have trained the neural network I've just shown you on 50,000 brain images, where they have taken fully sampled MR measurements, okay, brain imaging measurements. These are my reference images. They have simulated undersampled Fourier measurements with different encodings, what they call encodings here in Fourier spaces. Here the red lines or the red dots mean where I've actually collected the Fourier samples. So these measurements are simulated, and then they use the trained neural network to now reconstruct, okay, based on these measurements. These are 3 different examples. And so the second column, you see the result of AutoMap. The third column, you see compared to a conventional mathematical model-based approach as we have encountered at the beginning of the talk. Yeah? And this works, yeah. And this, I'm not showing you boring numbers now, but this also works qualitatively, again, measuring in terms of PSNR or something like this, much better than these conventional approaches. One thing maybe to say before I jump to the next type of approach that you might already question a little bit is, on the one hand, we are throwing away a lot of information here by just learning everything that actually some of the things we already know, right? We know that a Fourier transform is involved, but we are kind of forgetting it apart from the fact that we have these fully connected layers and we are learning everything. So this is a bit strange to do it like this. And of course, we pay for this by needing a lot of training images because we need to learn a lot. And by the fact that the size of the data and of the images that these kind of networks can process is also limited by the memory that the training of these neural networks takes, because I have huge matrices, a lot of parameters that I need to optimize for if I need to do if I have these fully connected layers here. Yeah. Okay, so this is a bit this is maybe not the best thing to do. Another way is what is called learned post-processing. And here the idea is you decouple the neural network from the inversion. You first do a super simple inversion, and then you clean up the mess that you have created by the super simple inversion that doesn't really take into account the measurement noise and the ill-posedness in your inversion, where you see all of these in the artifacts that you create in the image. And then you use the neural network to clean up the mess, yeah, to regularize in an after effect. And so in magnetic resonance tomography is super simple. It's actually something that happens a lot in engineering type of approaches, where you take your subsampled Fourier measurements, your undersampled Fourier measurements, you say this is a Fourier transform, I forget about the measurement noise, I fill up all the Fourier coefficients that I don't know with zeros, and then I invert the Fourier transform, okay? So this is zero padded, I fill up all the Fourier coefficients with zeros, and then I invert. And in mathematical terms, for, you know, in an inverse problems context, what this means is I compute the pseudo-inverse of the subsampled Fourier transform. And so this usually, the pseudo-inverse solution to inverse problems usually shows all the kind of artifacts that the forward operator T, or its inversion, features. And in this case, in the subsampled MRI, you see these ringing artifacts, these aliasing artifacts. And it, of course, doesn't regularize. So you have lots of noise and stuff like this also in it. And then you use a neural network like a UNet, a fully convolutional one, because you only need this to regularize, to then regularize this output and produce an image without the noise and without these ringing artifacts. Okay. And then you do some stuff here, which is not so important. And this also works. So now, first of all, you notice there is a big jump now in terms of number of training images. We only train with 1,400. These are two examples where I'm showing you here the ground truth. Here, the simple pseudo-inverse solution, so this or it's also called zero-filling solution. This is what the network does after it's fed with this simple inverse. And it works. And again, in terms of numbers, this works very, very well. Okay. Still, when I saw this for the first time, and I kind of still think of it like this, one of the things you feel a little bit awkward about or a little bit uneasy about maybe with this is that you first do something that is not really state of the art. You first reconstruct with a bad method, and then you clean up what this bad method has introduced in terms of artifacts and noise, noise enhancement and so on. So this is in a way not the most elegant way maybe to do things. I think more elegantly, and this is indeed kind of state of the art in deep learning solutions, is what is called learned iterative reconstruction, or learned unrolling is also called learned unrolling. So here you design a neural network inspired by what happens if you would have a variational model and solve it with an iterative scheme, let's say gradient descent. So you design, you can think of the layers of your neural network to almost mimic what happens when you iterate for minimizing an energy functional that corresponds to a variational regularization approach. And you design this in a way by setting up a neural network that intertwines the regularization with the fit, remember the data discrepancy term, the fit with the forward model. Yeah, so it incorporates both the forward model and the regularization in the neural network architecture. And this also works. Yeah, so this is now trained with approximately 2,000 images. And here is a comparison, is again ground truth. This is now computed tomography, just to link back also to what we've seen at the beginning. This is what you would get, again, simulating high noise measurements from the ground truth. This is what you get with the filtered back projection, which is the pseudo-inverse solution to X-ray tomography. This is what you get with total variation regularization, and this is what you get with the learned iterative approach. And you see, this is again the PSNR here, the numbers that I'm showing. There is again a huge jump. Yeah. So this is really fascinating. Yeah? I think it's really fascinating. It's really something. I mean, inverse problems, real inverse problems that we're solving are super tough to solve. And these type of qualities in the reconstructions we have really not seen before deep neural networks came around. Still, there are lots of worrisome things. Yeah? One of the most worrisome things is that there are almost no theoretical underpinnings for this stuff. Yeah? We have all the time when thinking about how to solve inverse problems, we are using, either our kind of functional analytic mindset to turn ill-posed problems into well-posed ones through mathematically sound regularization and so on and so forth. It's not at all clear with the type of approaches that I've shown you. Indeed, also members of the FoCM community have actually shown that there are intrinsic ill-posedness and instabilities in deep learning solutions to inverse problems. And we have seen this also more generally with deep neural networks, this deep fake and so on, these adversarial examples, and so on, these adversarial attacks. So this is happening also in inverse problems, in these deep learning solutions to inverse problems. There is also the interpretation of the reconstruction model is in general missing. Yeah? or only known asymptotically. For instance, for these learned unrolling schemes, the last example that I've shown you, we know that asymptotically solutions converge to conditional mean in the infinite data limit. But that's the infinite data limit, and is also the perfect training limit. Yeah? Data consistency is also in general not guaranteed. It's not clear that what the neural network spits out indeed lives in the range of the forward operator. And usually these type of deep learning solutions to inverse problems, they require lots of supervision, lots of supervised training data, which can be problematic in inverse problems where they appear, for instance, in scientific or medical imaging, where we cannot cover confidently all the solution space because we don't know. We use imaging often also as an explorative tool. Okay, so this, I hope, kind of sets a little bit the scene for now thinking about an alternative. And the alternative, in my point of view, is to start with a sound mathematical model and then to plug and play with data-driven components like deep neural networks as they come in handy, as they might give us better solutions, yeah? But still not take us totally out of our mathematically sound zone, okay? So this is the framework. So we start with, variational approaches, PDEs, and so on, for which we have mathematical guarantees, for which we have interpretability, and so on and so forth. And we use learning only to complement what we cannot model well, in a way, ideally, that the resulting inversion model is still preserves some mathematical guarantees of the general model that I've started with, and also in a way that training is more feasible also in small data regimes, in regimes where I don't have a lot of ground truth data that I could train with, okay? Okay, so the example I want to look at is learning the regularizer in a variational regularization context, mainly motivated by the fact that this regularizer really should capture structures in solutions that I would like to compute of my inverse problem. Statistically, these variational regularization approaches in certain cases can also be interpreted as the maximum a posteriori estimator in a kind of Bayesian inverse problem setting, in a statistical setting, in which case the regularizer is the negative log of the prior distribution that I assume my solutions to the inverse problem should follow. So there is a lot of prior assumption in it that make up how I should choose the regularizer. And this is super tough to choose the regularizer. Yeah? Total variation is limited, and any kind of regularizer that we can mathematically model is limited. So why not think about making this more data-driven? And there are lots of motivations why we want to stick to this variational model, and I've pointed them already out on the previous slide. Okay, so this is what I want to do. And when doing something like this, of course, the first thing you do is you look at what other people have done and how people have thought about learning a regularizer. And actually, almost 10 years ago, I've also started looking into learning regularizers from data through a bi-level optimization approach, where you say you have your variational model, you parameterize the regularizer in some way. Usually these are kind of more low level parameterizations of this regularizer because of computational limitations that you have. And then you optimize the parameters in this variational in this regularizer by evaluating the fitness, the quality of minimizers of the variational problem against some evaluation criterion, some objective function, capital F. And this is also why it's called bi-level optimization, because you optimize the parameters lambda with respect to some for some objective function, where the parameters themselves depend on this variational problem. Okay. Another example are black box denoisers. This is something that is super hip at the moment. Actually, two of these plug and play or regularization by denoising approaches have won the SciEM Imaging Sciences Activity Group Awards last year. And here the idea is image denoising. A lot of work has gone into image denoising. There are lots of denoisers out there. Can we use off-the-shelf denoisers and turn them into regularizers for solving an inverse problem? For instance, what I'm showing you here is regularization by denoising, where there is a particular way for a certain class of regularizers, for a certain class of denoisers to turn them into really mathematically sound regularizers for inverse problems. Yeah? And you could think of also, for instance, using as a denoiser a deep neural network. Yeah, you could also do that. And then something that is already quite classical in a way is to say, I know what my prior assumption, roughly speaking, is on the solution. It's a sparsity assumption. I assume that my solution can be represented in some kind of sparse basis or dictionary, but I don't know what the dictionary elements are, and those I learn. Yeah, I parameterize them in some way, and then I optimize also over them. And then there are neural networks, and now I'll show you as an example a neural network type of approach. And so this is a joint work with a couple of people. So what we have done, we have started working on this about 2 years ago. And we called our type of learned regularizers adversarial regularizers, so learned adversarial regularizers. And so this is joint work with Marcello Carioni, Søren Dietmar, and Shubho Mukherjee, who are all three are postdocs here in Cambridge. Sebastian Lunz is a former PhD student of mine. He is now working for a hedge fund, unfortunately, but he's happy, it's fine. Ozan Öktem is a colleague of mine from KTH in Stockholm. And Zach Shumyalov is actually a Cambridge undergraduate student who was just amazing so far. He has worked with us for 2 summers, and it was just amazing what he has been doing. Okay, so how do we train a regularizer adversarially? How we thought about doing this is almost training the regularizer to be almost like a classifier. Yeah. So I take my regularizer and I show the regularizer examples of what I call here good guys of images or structures and images that I want to preserve, that I want the regularizer to favor, which in other words means, if you think about that in a variational context, the regularizer for the good guys should be small. The regularizer shouldn't penalize those, right? And on the other hand, I show the regularizer examples of what I call here bad guys, which are reconstructions that show the measurement noise, that show all the artifacts that are due to the ill-postness of the forward operator capital T, and that are in the context of, in the framework in which we are looking at, are the pseudo-inverse solutions that I compute of my inverse problem. Okay, so this is the setting I'm in, and I'm in particular looking at this, which is maybe already given away here with the pseudo-inverse. I'm looking here only at linear inverse problems, okay, which include magnetic resonance tomography and computer tomography as TOR examples, and the main example I'm showing you here is computer tomography. Okay. And I want, therefore, the regularizer to penalize those bad guys. So I want the regularizer to be large. So my training set, in short, for training this regularizer consists of two sets. One is the set of the good guys, is an empirical distribution of the distribution PU, okay? And one is the set of bad guys, which again is a finite number of samples from the infinite distribution Pn, okay? So Pu are the good guys, Pn are the bad guys. And now the question is, for training or for now learning a regularizer, I need some optimality criterion, right? That captures exactly what I've just said. And nicely enough, the quantity that does that, it turns out, or a quantity that does that, is the Wasserstein distance. Yeah? And so this indeed is the Wasserstein distance between those two distributions, Pn and Pu. And you can see this by looking at, in particular, the one Wasserstein distance between Pn and Pu. And you can see that by looking at the corresponding Kontorowicz dual formulation, where R is my desired regularizer, is the one that maximizes this difference here, which means it I want an R that is large when fed with the bad guys, and that is small when fed with the good guys. Okay. And so the neural networks come in as a parameterization for this regularizer R that I'm looking for. And we use as a parameterization off-the-shelf convolutional neural networks. Yeah, so my regularizer R theta is an off-the-shelf convolutional neural network. And then I add a small L2 squared term in the general case to guarantee that my regularizer is bounded from below. In the case where I'm choosing my neural network, my psi theta, as a convex convolutional neural network, I can do this. There are these beautiful input convex neural networks. Then I'll actually have a strongly convex regularizer by adding this small L2 term. And then I train the neural network part of the regularizer, the psi theta, by using this so-called Wasserstein loss, which is an approximation to the one Wasserstein distance, where I've now replaced all one Lipschitz functions by my particular parameterization. And I also take the one Lipschitz constraint and I put it here as a penalty term. Okay. And now I'm kind of done. Yeah. So my recipe is I create training data of good guys and bad guys. How I do this depends on your application. Then I train the regularizer in this adversarial fashion. And then I deploy it. And I call it whatever comes out. I call this the learned adversarial regularizer or learned convex adversarial regularizer. And I put this back into my variational problem. And this is now my learned variational problem, my variation problem with the learned regularizer. And so the beautiful thing about that is that we still get well-postness. We get basically well-postness for free. And here I'm showing you this for the convex version of the learned regularizer. We get existence and uniqueness just by a strong convexity. So there is nothing really fancy here. We get stability. Yeah, we get robustness through just basically solving it with a variational regularization approach. We get convergence in the sense of if the regularization parameter goes to 0 and the noise level goes to 0 with a certain rate, then I'm actually converging to an R minimizing solution of my inverse problem. This is a typical thing we want to show about regularization for inverse problems. And the variational model can be solved with a converging iterative scheme. Yeah? Okay, so let me jump over this. We can show a little bit more about the learned regularizer in terms of what it actually does, but let me finish by showing you an example of how it actually is doing. Yeah, and I now pick. I mean, I've shown you at the beginning an example for this high noise CT example where we have seen that there is a huge jump between learned regularization and total variation regularization. But now I want to show you the result for a super tough computed tomography example, which is limited angle tomography. So here, and this is just a toy thing to show you what limited angle tomography is. Here, my measurements that I take are missing a whole range of angles. So a whole range of line integrals are totally missing. Yeah, and in the case that I'm showing you here, there are actually 60 degrees of angles are missing. And then I show you simulated measurements of this kind based on the Mayo Clinic OpenCT dataset, okay, which is an open dataset of high dose, so low noise CT measurements that I can use as my ground truth. And I show you the filtered back projection solution, which is an example of our bad guys, right? This is the pseudo-inverse solution to the limited angle tomography problem. I show you as a prototypical classical variational regularization solution, total variation regularization. I show you the result of the adversarial convex regularizer, and I show you an example of a learned unrolled scheme, okay, which is this learned primal dual approach. Okay. Now, let's see what happens. So on the left is the ground truth. On the right, this is what filtered back projection gives you, and you see the limited angle, right? You immediately see where you haven't measured things, right? Because this is where you can't resolve the reconstruction. And also now look a little bit at the quality measures here. This is like 21 something now. Now this is the total variation reconstruction. This is already a huge jump, right? So if I go back and forth, so this is already quite good. There is no learning yet involved. This is just classical total variation reconstruction. This is what you get with the learned convex, the adversarial convex regularizer, so the learned convex regularizer. Yeah. So again, visually, one thing you notice is that you get rid of this kind of artificial blocky artifacts that are very typical for total variation regularization. And you make another jump in the PSNR. And this is what you get with the learned unrolling, okay? And so if you look at the PSNR, it's much better. If you look visually also on the first glance, this looks much better somehow. But if you go back and forth enough times, you actually see that there are really boring things happening. And this is, I really think, looking at tough inverse problems like this one, it shows where the theory is and where the theory is not holding up. Because if you look at this here, then just look at the bone structures because they are kind of obvious. This doesn't look at all like the one on the left, right? It really has deformed the anatomy, which is not good. And this is something that as a mathematically sound inversion approach shouldn't be doing. And indeed, our adversarial regularizer is not doing this. Okay, so let me go over this. I just wanted to share with you some work in progress, but I've talked too much at the beginning, so I'll not do that. There are lots of open problems still, but let me just wrap up and just say a few more words. So I really think deep learning is a powerful tool for inverse problems because of its capability to be very adaptive to data. It really captures well what the main components in a data set the main structures in images, and it can use this in very effective ways. The most successful approaches are really those that combine deep learning with mathematical modeling, and there are still many open questions with respect to generalizability, universality of learned approaches, interpretability, uncertainty quantification, and so on and so forth. And of all the deep learning approaches that I've shown you, I've only shown you one for which we can actually prove well-postness. So there is still lots more to do. I think it's worth to be looking more into this because the results are just very convincing. Thank you very much. Thanks a lot for your attention. Thank you.
Well, thank you very much, Carola, for this very interesting lecture. So the talk is now open for discussion. Are there questions? So there's a question by our host, Albert, who should be able to unmute himself.
Yes, hello, Carola. This is Albert. Very nice talk. So, okay, you covered a lot of approach. So, for example, I mean, I want to know in all this first approach, is there any theory available or that you foresee about the amount of data, for example, that you need? You had method where you needed 50,000, another 2,000. What are these numbers? Is there any logic behind that? And so can you grab? And my other question is in concrete application, like tomography, medical application, how do you get what you call ground truth?
Yeah. Okay. Thank you, Albert. So the first answer is actually, I think, super dissatisfactory because at the moment, the amount of training images that we need is really something that is empirically determined with kind of some, again, empirical logic behind, in the sense that the more parameters that you have, the more training data you kind of need to train these models. The more degrees of freedom you have, the more training data you need. This is also why these fully learned models require so much more than actually all other three that I've shown you. So this is one thing. So it's not very satisfying. In terms of how do you get the ground truth? So this is something that, thank you for the question, because I actually didn't emphasize enough. So in all the approaches that I've shown you, apart from our adversarial learned regularizer, these are supervised training approaches in the sense that the ground truth really needs to correspond to the measurements that you are taking. Yeah, so you need to have a ground truth there, which again in realistic scenarios is often not the case, because we use tomography or whatever imaging to explore maybe often unknown things, so we don't have a ground truth often. But maybe we have very good high quality measurements with the same technique of either phantoms. So in MR and CT, there are phantoms that people build, so artificial things that they put into the tomograph that could be used to train our adversarial regularizer. Or you have organisms that you know their structure of through other things, through biological theory, molecular biology theory, or something like that. It really depends a lot on the application, but the nice thing about our adversarial regularizer is that the data that we want to apply the variational reconstruction approach later on does not need to correspond, does not need to be paired with the ground truth images that we have in the training set. So these can be decoupled. Yeah, thank you.
Thank you very much.
So then the next question was by Wolfgang Dahmen. should be able to unmute himself.
Yeah, hello, Carola. Thank you very much. Very interesting talk.
Thank you.
My question goes a little bit in the same direction. So when these comparisons are made, I hear very little about the necessary computational work and a comparison of the actual computational degrees of freedom going into it in compared to the competitors. So if I hypothetically just invest the same amount of money, so to speak, in terms of computational degrees of freedoms and also willingness to compute the hell out of it, would the neural networks still give you spectacularly better results? I mean, I'm asking what the magic is. Why is this kind of parameterization so particularly good for the things you are trying to capture?
I mean, I think the
comparison, so to speak, given also the fact that there is always a certain uncertainty in optimization success, right? I mean, it's always a non-convex problem, and you may be stuck someplace. And how do you know that you are really exploiting the full potential of what happens?
Yeah, this is a really, so thanks a lot for the question. This is a huge question in a way, because this is really hits on some of the foundational questions around deep learning, right? So the reason of why I'm so hopeful that these neural networks really have some future for inverse problems is really just at the moment empirical evidence in the sense that really when I've first seen some of these results in papers, we have never dreamed of being able to solve inverse problems in that way. And the key here really is the over-parameterization, the high over-parameterization that allows, even if they are just computing some local minima, I don't know, they're still perform super well. I remember one of the first talks I've heard on the variational networks, which are some type of learned unrolling, where the speaker, Tom Pock, said, well, I don't care if I compute the local minima because they're all performing really well. Much better than our total variation type of approaches. In terms of, yes.
But again, in order to achieve that, you basically are emulating a descent in a continuum, because your capacity is so good that you could ideally do an ideal descent of an energy in a function space, which is a simple thing. It's a convex functional then. So I can believe that this is true. But if you invest the same amount of work and the same number of degrees of freedom in something that you computationally understand very well, would the results still be better? I sort of doubt it, I must say.
The key here, so I'm kind of with you here, Wolfgang, because the adversarial regularizer that I've shown you, we are at the end solving a variational problem. Every time we want to solve the inverse problem, we are solving a variational problem. But I would say this is a big disadvantage of our approach, because the big advantage of using deep neural networks in a context like this is that, okay, the training is super tough and computationally very, very costly. But you do this once, ideally, right? Or maybe you update at some point and you do it another time. But then you can apply it a lot of times, and it's really just an explicit, which is still going to be limited by how large things can be. And this will not be for free, but it's still much cheaper than doing gradient descent or any kind of variational problem solving.
But in a case where you don't have a ground truth, do you have any way to decide whether the outcome of your computation is actually good or not?
There you need to work with the domain experts. This is where you need, because in a way I've told you for the training, we don't need the ground truth that pairs with the measurements, okay? But you're right, for validation, how do you validate? Yeah. This is where you need the domain experts. Either they have some simple toy mechanisms that we can use for validation, and then this is, then that's okay. or they need to evaluate through their experience.
Okay, thank you.
Thank you.
So then maybe briefly, there was another question posted in the chat by Jocelyn Etienne. In ACR, I don't understand the usage of pseudo-inverse of T as a bad example. I thought they were the original images used for the learning. Also, since these pseudo-inverses are already not so bad, indeed showing the basic features, why doesn't it lead the method to be completely off?
Okay, so if I understand Jocelyn correctly, the question is why is the pseudo-inverse a good example for the method to penalize? So Jocelyn, what we tried at the beginning, actually, or maybe let's go back here. What we tried at the beginning is to choose as bad guys just noise, because this is another thing you could do. Why we and pseudo-inverse, by the way, as bad guys is just one example, because we know of a lot of inverse problems where we can't compute the pseudo-inverse even. So why I've chosen the pseudo-inverse in this case is because it shows some of the artifacts of my inversion that usually the regularization should penalize, that the regularization should take care of in a way. In tomography, you could think of streak artifacts or something like this. In MRI, I've shown you some of these ringing artifacts. So this is why I thought the pseudo-inverse could be nice. I don't know, maybe there could be other things. Something, by the way, that we've tried is to update the bad guys. Almost for those people who know generative adversarial networks, there's always a discriminator and a generator network. And our regularizer, you can think of somehow as a discriminator, right? And we could, at the moment, as a generator, we only use the pseudo-inverse, but you could use as a generator also other things. You could update that by plugging the learned regularizer back into the variational model, produce new solutions by solving the variational model, and then retrain the regularizer, the discriminator, based on the variational problem solution, and so on and so forth. So there could be, yeah, you could think of doing things differently or updating that and making it finer and finer. I hope I answered your question, Jocelyn.
Yes, well, I think so. Yeah, thank you.
Thank you.
Okay, so thanks again for the great talk. So now let's move on to our second talk today. And this talk is given by Bojan Mohar. He is a professor of mathematics at the University of Ljubljana, and he also holds a Canada Research Chair at the Simon Fraser University in Vancouver. He is working on various aspects of graph theory, and among the honors he received for his work are a Fulbright Scholarship, the Kitteridge Prize, the Euler Medal, and the John L. Singe Award. He is a SIM Fellow, member of the Slovenian Academy of Engineering, and also recently of the Royal Society of Canada. And the title of his talk today is Drawing a Surface, a Graph on a Surface. Please, Bojan.
Thank you very much for the nice introduction. While I prepare my first slide here. So it would be much nicer if we would have a real conference, but by now we already learned that online conferences can work as well, or seminars. And I hope I can give a presentation of an area that I work in for a long time, and that would be filling a more theoretical part of foundations of computational mathematics. So it's in graph theory, we try to understand a lot of times what are easy and what are difficult problems that appear, and the main breakthrough is to get the theoretical distinction between easy and hard problems. So I will go on with a special problem about how to draw a graph on a surface. More specifically, I will consider what is the genus of the graph. So if you, a short overview is that I will first start to try to motivate why the genus is interesting. It's generalizing the notion of planarity of a graph which can be drawn in the plane in a nice way. And I will try to discuss, is this something that one can compute actually or not? As it turns out, there are difficult problems here. So I will describe two approaches which emerged from similar types of problems. One is fixed parameter tractability, and the other one is about approximation algorithms. And you will see these 4 parts of my talk somehow going along. So first, let me start by mentioning planar graphs. So this is genus 0. A graph is said to be planar if you can draw it nicely, like the one I have on my slide here. In basic courses of graph theory, everybody learns the 2 fundamental theorems about planar graphs. So one is that if we have a graph which is planar, then this graph is 4-colorable. Now, colorings of graphs, this was some kind an old motivation that came. It was a 4-color problem, was a problem which simulated developments of early graph theory. And today we know that this is a true theorem, although there are still no easy proofs of this result. And another result in this area is a Kuratowski theorem, which describes this class of graphs, the planar graphs, as those that don't contain one of the 2 graphs which I've drawn here. So the K5 is a complete graph on 5 vertices, and K33 is a complete bipartite graph which has 3 vertices on each side and all edges between them. So these 2 graphs are non-planar. They cannot, if you draw them, they will always have a crossing. Actually, you can draw them with just a single crossing, although my drawing here has many crossings. But the Kuratowski proof that goes almost 100 years back, so in 1930, that a graph is planar if and only if none of these 2 graphs appears as a subgraph, what actually as a topological minor, which just means it sits in the graph, and then if you take a subdivision, you subdivide the edges of this K5 or K33 sometimes, maybe 0 or more times, then this would become a subgraph. In that case, this graph cannot be planar, and so it's a very well structured proof that the graph is non-planar. So that's the basic theorems about these graphs, but there are other results. So, and they make the class of planar graphs much more interesting. So let me mention one such classical result. This is the separator theorem. Now, it was proved in 1979 by Lipton and Tarjan. And it says the following: suppose I have a huge planar graph on n vertices. So this n will stand for the order of the graph throughout my talk, or for the number of vertices. And if you have such a huge graph, there is always a small subset, call it S, which contains only order square root n vertices, and separates the graph into 2 big components. So we say it's a balanced separator, meaning that the part on the left and the part on the right are about of the same size. Formally, you can say that both of them, none of them is bigger than, contains more than 2/3 of vertices, or you can say almost equivalently that each of them has at least 1/3 of the vertices. So it's both are comparable in size. And this set S, which is separating, is a very small. So separating means that there are no edges between left and right parts. So such edges don't exist. All edges are within this part or between S and A and S and B. Now, why would this be important? Well, in computing, it comes very handy. For instance, look at the following situation. Maybe you want to compute something about your very large planar graph, something that would be very difficult in general. And what you can do is you can just subdivide this graph by taking this small set S and subdivide it into two smaller subgraphs. So the induced subgraphs on A and B are smaller. And then A and B are again planar graphs. So you can, the separator theorem applies to them. So you can, again, you can take a separator of the left side, let's say into parts A1 and A2, separate the right part, and so on. You can actually then continue, separate A1 into two parts, and then the left part you can separate again and separate again, and so on. So, and you can repeat this until all these parts are very small. So you get this, all these parts are very small, and but they still have the most of edges. So you repeat this maybe log n times. Let's say you repeat such a thing log n times or log n times, certain number of times. That makes this pieces manageable, and then you can just do divide and conquer. So you can probably compute the whatever you want to know about your planar graph in these small parts efficiently because they are very small, and maybe constant size, maybe of size logarithm n or something, but you can really do even brute force computations on them, and then try to combine these solutions step by step and coming back to a nice solution for your original graph. So that's why properties like having separators are of great importance in theory of algorithms. And as it turns out, the same separator theorem actually works in a more general setup. So if you, instead of trying to draw graphs in the plane, which would be equivalently drawing them on the genus 0 surface, the two-dimensional sphere, you can look at the same thing on graphs which can be drawn on the torus or the double torus and so on. And then you come to the notion of the genus of a graph. So let me start motivating the genus also with another ancient problem in graph theory that goes back more than a century. It was a generalization of the four-color conjecture to general surfaces. In fact, Heawood proved in 1890 that if you have a graph which can be embedded, so drawn on the surface of genus G, then you have a small chromatic number. Then the number of colors you need to color this graph is bounded by this, let's say, strangely complicated function, but it's just roughly square root of G. So order square root of G colors that you need. So this generalizes the four-color conjecture because if you take G equals 0, this would give the result is at most 4, which was eventually a four-color conjecture. But actually, Heawood could prove the less or equal for any G which is bigger than 0. For genus G is 0, this was left open for almost 100 more years, but this one was actually solved. And then about 50 years ago, even this full conjecture of Heawood came to a resolution that not only there is inequality that Heawood proved, but also this is the best possible result. So in fact, if you look at the maximum chromatic number, the maximum number of colors you need for graphs of genus G, it turns out that you have equality here. So today we know this is equal. And due to the work of in that time, it became clear that the equality was really equivalent to the statement about the genus of the complete graph. So what is the smallest number of handles of a surface? What is the smallest genus of a surface you need to draw the complete graph? And it turned out that this is this formula in Ringel and Young's theorem. So it's roughly n squared over 12. So that's the and it's the exact formula with this ceiling function. So that was proved. That's called today. It's called Ringel and Young's. It says it speaks about the genus of complete graph, but it's also a map coloring result, and that's how this theorem is known. Now, if I try to discuss the genus, so let me mention the fact that I already implicitly noted. What are surfaces and what is a genus of a surface? So everybody understands what are some basic surfaces like two-dimensional sphere S0, or the torus, which I have here S1. Double torus would be S2, and then triple torus S3, and so on. So if we take this picture further and further, we get surfaces of bigger and bigger genus. So that would be surface of genus G. Would be obtained from the sphere by attaching G handles. There is also another family, infinite family of surfaces. They are non-orientable surfaces, and they start with a projective plane, Klein bottle, and so on, and they correspond to a connected sum of several projective planes. I'm not gonna speak much about non-orientable case in this talk, but everything I say works for non-orientable case with, of course, obvious modifications. So let me just define now what is the genus of a graph G. You look at the minimum number of handles, minimum G, so that the graph G can be drawn, can be embedded on the surface S sub G. So if it can be drawn on S2, then the genus is at most 2. Maybe it should be even smaller, but it's the minimum G is called the genus of the surface. And so that's one thing that we want to understand. Now, how would you decide if a given graph can be drawn on a given surface? Well, luckily, there is a combinatorial apparatus here. So when we speak about minimum genus embeddings, it suffices to look at so-called two-cell embeddings. A two-cell embedding means that if you draw the graph on the surface and then remove your drawing, the surface will split into faces, and each of these faces is an open disk. So if you, let me think of this drawing here, that I identify left and right side and identify top and bottom. So then you get, after these two identifications, you get the surface of the torus, so genus 1 surface, and this black graph is a two-cell embedding. So what is characteristic for this two-cell embedding? You can look. So here, if you look at this boundary, this is a face, and it's an open disk. It's homomorphic to an open disk. Well, look at this one. This one is a little bit more complicated here. if I trace the boundary, I re-emerge on the other side and I go here. So this is another face, but it's not so simple as this one. So but as an open subset of the surface is a disk, you see. And similarly, you can look at faces like this one. Let me try to trace the boundary of this face here. Again, you see it has a singularity. It touches itself, but inside of this face is an open disk. So this is the notion of two-cell embeddings. And two-cell embeddings have really combinatorial description. You don't really have to draw the graph on the surface, but you can just look at so-called local rotations. So what's a local rotation? For each vertex of the graph, you describe, so this is my vertex, you describe this local clockwise order on the surface. So now, once you do that, you can actually forget about the surface. Forget about the upper picture, just look at these local rotations. And you see, like here on the right, if I try to trace this face, I see this face will clockwise continue with this edge, and then with a clockwise rotation at this vertex, it will continue with this edge. And here, it will continue with this edge, and so on. And so you can trace what the boundary of this corresponding face would be. So just having these local rotations at each vertex, you can trace and you can find what will be these boundaries of faces. Now, when you count these faces, let's say F is the number of faces. When you count them, then you can say what surface you are in. So because there is so-called Euler's formula, which relates the number of vertices, the number of edges, and the number of faces to the genus. It's this simple linear inequality, which gives, so it would give genus 1 for, if you count for the example at the top of this slide. Now, there is one other message from this Euler formula. If you look at the genus expressed in this way, you see the number of edges and the number of vertices of each graph. This is something you don't change. All you want to change is you find an embedding which will have certain number of faces. And if you want genus to be small, you want F to be large. So that's the message. You want an embedding with many faces. And this is pretty difficult. If you want embeddings with very small number of faces, this is usually very easy. Sometimes, mostly with nice graphs, you end up with embedding which has only 1 or 2 faces, depending on some parity arguments. But finding many faces, this is difficult. Now, we can go back again, back to the 1970s. And already in the 1970s, there were fast algorithms known how to determine if the graph has genus 0. So genus 0 again means that you can draw it in the 2-dimensional sphere. So this was linear time. Linear time is the holy grail. So this is something, if you have n vertices, this just means O of n. So it's the same time that you just see the graph, right? You don't need more. It's in the same time you can see if the genus is 0. So planar graphs are easy to recognize. Of course, the algorithm is not that trivial. It's difficult to describe, but it's very efficient and very useful for practical applications. People extended this also to involve Kuratowski's theorem. So if a graph is not planar, then you find a Kuratowski subgraph, one of these two obstructions. And once you find that, you you can be sure that you didn't make a mistake in your computation, right? Now, people tried to look, well, can I do the same for the torus, so genus 1? And that could prove to be quite difficult. So the first result of this type was by Filotti, Miller, and Rife. They actually published the stock in '82. They published a paper which showed that for every G, there is a polynomial time algorithm. So for G equals 1, this would be n to the 188. So this, and it shows that even G equals 1, so the torus, it's far more complicated than the sphere, than the planar graphs. And to be frank, there was later, when de Merwold, maybe 15 years ago, tried to implement some of these algorithms, and she found all sorts of oversimplifications in these algorithms. So it's not really clear that even this complicated time frame worked. Now, Gary and Johnson define this genus problem. So what is the genus of a given graph on the list of the basic fundamental problems, which at that time were open. So today there are, I think, 2 of those 10 problems remained open. One is the isomorphism problem, and another one. But for the genus problem, it was resolved about 10 years later by Thomassen, who proved that it is NP-hard. So genus is hard, and even I proved in 2001 that it's hard even for a set of graphs which are called apex graphs. So what's an apex graph? Apex graph is a graph which looks like a planar graph. So you have some planar graph, a graph which is easy by this mean, and then you have just one additional vertex, just one more vertex. So this one is adjacent to some of the vertices here, and of course the graph need not be planar anymore. But maybe you would think that because I can easily deal with this graph except for one single vertex, that the genus of this graph would be easy, but still it is still NP-hard, even for this very simple class of apex graphs. Now, a big success was so-called FPT solutions. So this is today known as the fixed parameter tractability. So you take genus G as the parameter, and then for every fixed G, you can do something. And in fact, one of the great outcomes of Robertson and Seymour's theory of graph minors was a cubic time, polynomial time algorithm. So now the degree of the polynomial is independent on G. So this is O of, it's some function of G times n cubed algorithm. And of course, this f of G is probably exponential in G, because otherwise we would have very efficient solution. So, but this is called fixed parameter tractability. Now, what their algorithm is using a version of the Kuratowski theorem. So there is a general Kuratowski theorem for every surface. You have a set of graphs replacing this K5 and K33, and then you just check for their presence. And Graph Miners project found cubic time algorithm for such tasks. I proved with a different method, so which was more constructive in 1996, that actually there is a linear time algorithm. So you can replace this with a linear time. Of course, you still have a big constant in this O notation. But for every fixed G, there is a linear time algorithm to decide if you can, if your graph has genus at most G. So this is once you have a difficult problem, this is one avenue that you look at fixed parameter tractability. The other one is showing below, it's approximating. And I'll try to say in the second part of my talk, I'll try to say something more about computational issues about genus approximation. So what do we mean by saying I want to approximate, or I want an approximation algorithm? Basically, I want to compute the genus of the graph, but I may find an embedding in the surface SG, which is maybe a little bit bigger than the minimum possible genus. But on the other hand, I don't want it to be much bigger. So I allow for this factor. Usually you don't say C times G, but 1 plus C times G. If C would be 0, this would be exact. But if C is, let's say, 0, 1, this would be only 10% worse than the minimum, the absolute minimum. Although we cannot say what the minimum is, we can say maybe we are close to the minimum. So that's the idea of approximation algorithms. However, this is still widely open today. So the best C here depends on different parameters. So there is one. There are results which say where C is not a constant but another constant, and then times a function of n. So this is so we get approximation, but if you have many vertices, this approximation won't be so good. It appears in a factor, right? And another one where this square root of n is replaced with polylog of n was obtained also, and this was this is basically today the state of the art. Now, when we look at the approximation algorithms for graphs, I have three different regimes which I think behave differently. So that's the first regime is the sparse case. For instance, cubic graphs. If you just look at graphs which have all vertices have small degree, let's say 3, this and want to approximate the genus within a constant. So you want maybe you want an answer which is at most factor 2 or factor 100 or factor 1000 away from G, but independent on G and independent on your graph. So I want this constant factor approximation. Here, so this I believe there are efficient algorithms, and I have some preliminary work on that, but nothing conclusive yet. And I conjecture that this case is actually hard in the sense that approximation to a very small factor, so where this C would be very small, it's not possible. This is called APX approximation hard. So there exists some positive C that we cannot approximate this efficiently unless P is equal to NP, of course, in which case everything can be efficiently computed. Now, the sparse case, it's probably the kink case in this case, but there is the intermediate case where you can prove you can easily find a constant factor approximations. For instance, taking series 24, I can prove that there is such approximation. I would like to have this constant maybe just equal to 1. That would be great. So this is still I can show there is a constant factor approximation, but it's still widely open how good you can approximate. And so these two are intermediate. And then there is a dense case. So we say a graph is dense if it has quadratically many edges. So there is some constant alpha, which is positive, and we have a graph on n vertices, which has at least alpha n squared edges. The complete graph would have roughly 1/2 n squared edges, but there are, of course, many edges which would have at least 1% of all possible edges. So for those graphs, we call them dense graphs. And I want to go into details to show a little bit about the methods which actually give a very nice approximation algorithm for this dense case. Now I'm at the threshold now to go into this dense case. I would be happy if there are some answers at this point. So let me just ask if there are some questions. Maybe moderators can look if somebody raised the arm and they can unmute. No, so if not, let me proceed. So I'll go with the next step about the genus of dense graphs. So suppose just think of any constant. Let's say alpha is 1 over 1,000, so it's 0,001. And I want to look at graphs which have at least alpha times n squared edges, and I'm trying to say that the genus approximation for this class of graphs is manageable. And here is the theorem. So this is a theorem by Yifan Ying and myself from 2018. It's quite recent result. This was a Fox paper, but the full paper is still on archive and in the submission process. So now the theorem which we proved is that we can really nicely approximate the genus in this regime, and this is what is called PTAS. So PTAS is the holy grail in approximation algorithm. It means polynomial time approximation scheme. And this means the following. So for every epsilon, we can say there exists an epsilon approximation algorithm. So the constant C, which you saw in the definition of approximation algorithm, could be as tiny as you want. So you get 1 plus little epsilon factor. So very tiny factor. So for instance, like this. So you want this for every epsilon. And the PTAS is efficient. So that's this E in front. PTAS is efficient if the complexity, if the time complexity of such an algorithm is a fixed polynomial. So here in our case, it's quadratic time complexity with the constant factor which may depend on epsilon. So for every epsilon you get C sub epsilon times n squared is the necessary time that you need to have, and then you can efficiently, in this time, you can approximate the genus. Now, I'll try to describe some of the ingredients of this polynomial time approximation algorithm. The basic observation which makes this is an easy observation, makes the thing work, is that if you have quadratically many edges with this constant alpha, then the genus is also quadratic. So genus is of order n squared. So it's roughly between 1/6 n squared and another bigger constant n squared times alpha. Now this is an observation, but still, how would you distinguish where in this constant range times n squared your genus is? Now here the basic result is the following, which you could say that if you normalize the genus, so this would be the normalized genus would be just the genus of the graph divided by the square of the number of vertices. So this is some constant, and this constant is continuous. Well, what do we mean by continuous? I will explain in the next slide. And also to do this, we need something that we can approximate the graph G by a small weighted graph, which you can then use to determine this exactly, this genus. So here is what I call view from the sky. So you look at all the set of all graphs from the sky. So this is this big blob. So here we have infinitely many graphs, small and large, and so on. And then we can turn this set into a metric space by defining the so-called, this is called cut distance. So we can define a distance between graphs, the cut distance between any two graphs, G and H. This could be graphs, one could be very big, one could be even much bigger, but you can still define a distance between them. And this distance, with this distance, you get a metric space between graphs, and you can consider a convergence. So all distances are between 0 and 1. Let's say you can get it like that, and then you can say also define convergence. And this distance, this metric space is not complete, but you can take a completion, and the completion is what is called graphons. So if you take a completion, you get a complete metric space, and you have a well-defined notion of distance between graphs and distance between these ideal points that we added to the space. So this notion is pretty new. It's maybe less, it's about 10 years, 10 to less than 15 years old. And it forms so-called theory of graph limits. That's was developed by Laci and together with many collaborators. So he had many people working with, and they together published series of papers, and Laci also published a book on graph limits. And it speaks about this space, this view from the sky. It's a good opportunity this year to mention Laci, who actually got recently was awarded the Abel Prize for 2021, and it's really amazing. So, and of course, this theory of graph limits was one of the ingredients in the citation for his prize. So this is something that looks pretty complicated, but it's from the distance, from the sky, you see the graphs behave nicely. And it's important that this metric is kind of efficient. So it goes together with another big result in combinatorics and graph theory, with the regularity lemma. So it's this was regularity lemma was originally obtained by Semeredi. Actually, Semeredi also got Nobel Prize for the influence he made with this, essentially for the influence made by his regularity lemma. And what regularity lemma says, it's about large, dense graphs. Well, you can think of it as also for not so dense graphs, but then it doesn't say so much. But if you have a large, dense graph, then regularity lemma says the following. You let me try to first read the conclusion. So it says that you can partition the vertices of your graph into sets V1 up to Vk, where this k is bounded by a certain constant m. So this is a huge constant, and you can add, initially you can add two parameters. You can add that you want the number of parts here not to be too small. So I want maybe at least m parts, at least 1,000 parts. And I want something which is playing the role of epsilon, similar epsilon I had before. But so you think of this as a small real number, so it's tiny in the sense of analysis. And then it says that there is there is a constant m, so that every graph which has sufficiently many vertices can be partitioned into k parts, where k is bounded within this constant range, and all parts are about the same. I guess, well, let me try to draw this on this. So you have this k parts. I'm always drawing 4 parts, so 3 is a little bit too small, and doing more is just messy. But in applications, this will be many parts. And then the following is true. So these are vertex sets, Vi and Vj. And the size of this Vi is about the number of vertices of G. Let me call it n again, divided by k. So they are about the same size. These sets are about the same size. And then the conclusion is that the graph, the edges between any two such pairs look like a random graph. So it's so-called quasi-random graphs, but they look essentially like a random graph. Of course, it can't be exactly that. So this random graph is not random, it's quasi-random, it's essential. And also there is a tiny fraction of pairs that can, for which it doesn't look like random graph maybe. So, but it's this fraction of pairs is tiny. So there are k-squared all pairs, but just an epsilon fraction is such. And again, this being almost random, it's also parameterized how almost. So epsilon, if epsilon is small, these are really, really very close to be random graphs. So this is the message of regularity lemma, that you can partition every graph into at most, let's say, 1,000 parts, and between each of these parts, the graph, the induced graph, looks like a random graph. There is usually the number of parts is at least. So this is a usual requirement is that M is bigger than 1 over epsilon. So if epsilon is like, so you can do that. And then this M could be very big. So it's maybe 1 over epsilon to 1 over epsilon, or maybe a tower of exponent, but it's a fixed constant. So that's the this is the partition that you get. And suppose for our genus problem that we have such a partition. So we compute such a partition. Then we know we would like to obtain an embedding of the graph. And what the goal is to find a drawing with many faces, you remember. So if you have many faces, they must be very short. So all you want to do is to have lots of faces which are either of size 3 or size 4, and this can be done. The first thing is that you have to solve a kind of triangle packing problem. So you want to see in this picture of this almost random graphs, how can you get triangles? Well, there will be just few edges within these sets. So those won't give you, so those can be somehow neglected. But you can get triangles if you have three parts, so VI, VJ, VK, and then some positive density of the edges between them. There will be many triangles between them, and you want to use them as faces when you draw your graph on a surface. So this would be this is the basic thing, and one ingredient in the proof is just to consider how to get as many possible and how to get this packing of triangles. And once you have as many triangles as possible, all it remains is this, what I have a green edges in this picture. And they, that would be also like a random graph. They have many cycles of length 4. And you want to use these cycles of length 4 as your faces as well. And then there will be some edges which we neglected because everything is only epsilon regular, epsilon approximate, but those don't change the outcome more than what one would desire. So that's the global picture how it works. So we first determine this maximum number of possible number of triangles that we could get. So we want to get C times n cubed. That would be the number of triangles which we would hope for. And we want this C as large as possible. And C, it turns out, is a solution of such a linear program. So there is a linear program where each variable corresponds either to a triangle in this auxiliary graph. This is now on this at most m vertices. And you have the densities of the edges. So these are, you look at the VI and VJ, and you look how many edges are there. So these densities play the role, and you can try to maximize the maximum number of triangles you could have in your embedding. And what we proved is that you can more or less use all these triangles to get a surface embedding. So this is how the algorithm goes. So we have, of course, the regularity lemma only speaks about very large graphs. So if you have a small graph, you do it differently. You can say, I do it brute force. If you have enough vertices in your graph, you find a regularity partition. There are efficient algorithms, quadratic time algorithms. Fries Cannon and Jacob Fox and others designed them. Terry Tao has actually a very efficient randomized algorithm. Just more or less constant time. I mean, it's linear time, but it's very efficient to find these partitions randomly. Then once we have that, you compute these densities and solve this fractional packing, this linear program. And then the next thing is how to find from those triangles, how to use as many as possible, and then as many quadrangles as possible to find a very efficient embedding. This goes again through, this is the core of the algorithm as well. So this uses notions of hypergraph matching algorithms. Very efficient algorithms have been devised. So this is another ingredient used in there. And then once we have that, we need to combine all these graphs on all these embeddings. So for each graph, we, let's say this was Gij, G12, we find something which has, it's almost an embedding with many triangles and four polygons. So this was the graph between V1 and V2. Or maybe G123 with the triangles with V3 as well. So this graph, you get something which looks almost like an embedding, but still you have huge number of these graphs, and you want to combine this into a single embedding of your single graph. So how you do that? So for instance, you take here, you have this from G12, and then you have this partial embedding from G123, or maybe G143 if you want. But you see, G1 has a vertex set V1, and G12 has vertex set also V1. So there are many vertices in common with these two graphs. So how do you combine them? Well, you basically just think of adding an edge between them and then contract this edge, and then this would give something which looks like local rotation around the vertex, almost. You know, it's missing something, but it's almost like a local rotation around the vertex. And you combine them all together to get something which is almost a local rotation, and then you prove that this is within this epsilon. So you finally combine this many embeddings, and then you find an embedding of genus, let's say G, which is of course bigger than genus of your graph. You don't know how much bigger, but we can show that it is at most 1 plus epsilon factor bigger. So that's what you prove, and the algorithm from this part of the algorithm is not difficult, but it's just need to verify that. Now I'm close to the end. We went over time a little bit, but I think I'm still within my time. And let me just make a short conclusion. I try to give you a picture of a fundamental computational problem. So this is considered a fundamental computational problem in graph theory, but it's used in many graph algorithms, which has progressed, which has matured during maybe more than 50 years now, and still we making progress and getting further with what it comes, and it's been tremendous progress in graph theory that made this possible. So one was, for instance, what I mentioned, graph minors theory of Robertson and Seymour, and then graph limits or regularity lemma that I discussed, and all this made these results possible. Now, there is a question which comes with results of this type. So this looks like theoretical. You see, I said if you have a small graph the small graph is something like, well, it's not 10 to the 10, it's more than the number of atoms in the universe. So including the dark matter, if you want. So it's this small means something which is small for me, but it's not small in practice. So what would this result say? So I can do let's say 0, 0, 1 approximation. So 1 plus epsilon, right? Approximation, which gives me a very good approximation, but only works really for huge graphs. Now, it's not the importance of these results, in my opinion, is not that they would be practical, but it's that it shows that it is possible to do it. So once you have that, you may get to a maybe even more efficient result, or something which is practically better. On the other hand, even this need not to be so bad, because theoretical analysis requires very large graphs. So it requires this, what is Jacob Fox calls this a wow function. So wow function is this, it's a tower of exponents. So let's call this 1 over epsilon k. So this is k, and it goes k to the k to the k to the k, k times. So this is just a simple tower of exponent, but the wow function is you do that again. So, and this is something unimaginably big, but still it could be practical in practice. So the Terry-Towers algorithm that I mentioned is just a randomized algorithm. So you try it, it works, and you get something that is practical. So you don't have theoretical guarantee yet because the proofs don't work, but it could be very practical as a conclusion. So that's the end. Thank you for the attention, and that's where I want to stop.
Thank you very much for this fascinating talk. So now the talk is open for discussion and other questions. So maybe one question to start with from my side. These estimates for the genus, I mean, this may be a rather naive question, but I imagine there are many uses also in algorithms when you have this estimate for the genus that is actually accurate, where you can actually use this for other purposes. So I was wondering if you could give an overview of that.
Yeah, so the genus, so it wasn't originally, for instance, planarity or maybe drawings with a small number of crossings. This was considered very applied project. So people were looked at large integrated circuits. So how to design a very large circuit without crossing, so that you could do electrical wiring nicely, right? Or I know very practical application from the Airbus industries. So when they were designing the airplane, they needed to do thousands of wires which go from the cockpit to the back of the airplane. So you see, where you sit in the airplane, all around you are just wires, more or less. So today it's maybe a little bit less, but it's a big graph that you're dealing with. So so they actually really used planarity algorithms for the design of the airplanes. Yeah, so this approximation, so far it's only theoretical, because as I mentioned, even for sparse graphs like cubic graphs, it is not understood well that we would even know, is it possible to approximate efficiently? So maybe it's not. So that's So certainly I conjecture that it's not possible to do something like this polynomial time approximation scheme, but or even that it's not possible to approximate with constant maybe 1/2. That would be so the C equals 1/2. That would be probably already impossible unless P equals NP. So yeah.
Thank you. So are there further questions? If not, then we close the session for today, and thanks again to both of our speakers for today for the great talks. And so that finishes the session, and now we leave the room open in case the people like to chat. And so then everybody has also the option to switch on the mic and camera if they like. And thanks to everyone for joining today.